Hello, welcome to the next video in a playlist that I'm calling General Linear Models Design of Experiments. And within this playlist, I'm creating little mini-series that deal with the different types of designs. This one is on balanced two-factor factorial designs without interaction. This part 4 of a 7-part series. And we're looking at the distribution of the sum of squares. So as a reminder, our model is y equals x star beta star plus epsilon. So it is a linear model. And then the design matrix can be broken down into the, a 1, an x alpha, and an x beta dealing with factor A and factor B. This is the grand mean. Epsilon is normally distributed. Mean vector 0 of covariance matrix sigma squared. Initially, the alpha and beta coefficients are fixed. The expected value of the sum of squares. So this is the sum of squares error, and it's the expected value. So, and I have a playlist called Quadratic Forms, and in there we calculate the mean and variance of a quadratic form, and it ends up being the trace of this matrix in the middle times the variance of y plus the mean of y times that matrix, of course the transpose, and then times the mean of y. So here, the variance is sigma squared I, so the sigma squared comes out, the I cancels with that. The rank associated with that is ABN, and A is the number of factors for factor A, B is the number of factors for factor B, N is the number of replicates within the crossed factors, and minus A minus B. And on the back page we'll investigate that a little further. So here it's x star beta star, I minus m, x star beta star, but this is I minus m is the perpendicular projection matrix onto the orthogonal complement of the column space of x star. So it projects everything into the orthogonal complement. So this has to be 0. Right? Or you can think of it as m times x is x, and then x, so you get x minus x, which is 0. So the expected value is this. And then you can divide that to the other side and get an unbiased estimate for sigma squared. So here's the mean squared error for factor A. So it's the sum of squares for factor A. And then using the formula that we derived in, the mean of a quadratic form. So it's the trace times the variance, mean, this matrix, and the mean of y. This is sigma squared I, sigma squared comes out, trace, so this is A, and this is minus 1. Here, M alpha minus J is idempotent, so you can take it times itself, and then this last piece kind of untranspose it, and that's what we get here, and then this. So let's look at this a little further. Let's just look at what we have here, and we'll call that star and bring it down here. So we have m alpha minus j, which is this, and then we're going to expand this to what we said it was up here. Okay, so here the m alpha minus j times 1 is 0, because this projects onto the orthogonal complement space of 1, and x is orthogonal to m alpha minus j, so that's 0, and so we're only left with this piece here. Now when we multiply this in, the m alpha x alpha projects it back onto itself, so we get it back, and then this is whatever it is, j times that. Now if you do the math on this right here, remember the form, or of the format of x alpha, and then if you take it times this vector, you're going to get it's going to be alpha 1, alpha 1, alpha 1 n times, and then alpha 2, alpha 2, alpha 2. And so you're going to get a vector of these components where the components repeat n times. But then when you pre-multiply it by j, which projects it onto that column space of 1s, it's going to be the mean of those components times 1. Okay. Now we'll use this one here because it's easier to see initially. So now we need to take this transpose times this. So this was star, and this is star transpose star, which is this. Now when you multiply this out, this is here, and then when you multiply this times this, and this times that, and then that times that, two of those terms cancel, and we're left with just one of those. Now here j is idempotent, so you can take it times itself and create two, j times j is, it's just j. But then you can kind of untranspose this left side into what's here, right? So j alpha, x alpha, alpha, and then this is the untransposed. Now this creates an identity matrix times bn, and that's what we get here. Well, and then this is going to be the squared things, right? I mean, j projects it onto the 1 vector, and then that times itself, you're going to get something squared times that 1 vector. And then, so then when you do this, you end up with this. I'm skipping a few steps, but make sure that you can go from here to here. This is the expected value of the sum of squares for factor b. And again, we would use the formula, the trace times this. And I'm going to skip this part, would generate sigma squared times beta 1, and then this is the piece that would, we would get over here, the quadratic form. Well, then this, doing something very similar to what we did here, would boil down to this in scalar form. Now, the distribution of these, so we just calculated the expected values. Now, I have a playlist called Quadratic, and in there we derive the distribution of quadratic forms, assuming the vector is normally distributed. Now, one thing that makes this derivation easier is if your variable is multivariate normal and has an identity matrix, it's a I, then this calculation is much easier. So I trick it, instead of saying y is multivariate normal with this mean, and covariance matrix is sigma squared times it. So if you divide by sigma, it gets rid of that. Then this derivation is like so easy. So then the sum of squares there divided by sigma squared, which is this, right? The sigma squared can be brought into the pieces, and then that is normally distributed with this. So then it's quite easy to show that this is distributed with a central chi-squared with degrees of freedom, whatever the rank of I minus m is. And we'll look at that in a second. Sum of squared of errors, or sum of squares for treatment A divided by sigma squared is this. And of course you can take those into the y's and do the same trick, and you're left with this. And this quadratic is what you get from here. Oop. Yeah, from here. And then we showed that is this. And that's why this is in the non-centrality parameter. So this is the rank, this is the non-centrality parameter. Then you can show that the sum of squares for treatment B over sigma squared is a non-central chi-squared with rank this, non-centrality parameter this. And this formula is, the derivations on the previous page. Now the degrees of freedom associated with these is the rank of this matrix here in the middle of the quadratic form. So let's look at that. So the rank of J, now since J is idempotent, it's also equal to the trace. And the trace, you can move things around. So if we move that to the back, well, this is the identity matrix. This is a 1 by 1 identity matrix. So the trace of 1 is 1. The rank of mx, since that's idempotent, it's equal to the trace, and then that can be taken to the back, and then you have an A by A identity matrix. So the sum would be A, the trace A. Here, same thing. This is idempotent. It equals rank equals the trace. That's a B by B identity matrix. So the trace would be B. So now the rank of the degrees of freedom for the sum squared error is the rank of I minus M. And M in this mini series is M alpha plus MJ minus J. I didn't say that right. M alpha plus M beta minus J. And then that minus changes all the signs. And since this is idempotent, it's the trace, and the trace is just the sum of those. And that's where we get ABN, right? This is an ABN by ABN identity matrix. And then A, B, and 1. Same way here. Rank, this is the equal, since this is idempotent, it's equal to the trace, and that's A minus 1. Degrees of freedom for sum squares for treatment B, or factor B. The rank, since it's idempotent, is equal to the trace, and that's B minus 1. Now, in the next series, we're going to look at F-tests, and these chi-square random variables have to be independent. And I have a couple different videos on testing the independence of quadratic forms, and it boils down to just multiplying the matrix in the middle of that quadratic form. So here, let's multiply it out. This times this times that, M alpha and the MJ. Now this is just M alpha, this is J. Since this is the perpendicular projection makes on the whole column space, and M alpha projects onto a subspace of that, M projects it back onto itself in the same way with here, and then everything cancels, you get 0. Now to show that the sum of squares for treatment B is independent of the sum of squares error, we show that these are equal in a very similar fashion, and it is 0. Well, that's all I have for this video. In the next video, we'll look at F-tests. And hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.